Howdy. So November, No Shade November was there, and I got myself this little mustache. Thinking about cutting it off, but got to keep it for a while. Let me know what you think. All right. Anyway, today we were talking about orbital velocities by studying Venus and not Venus, but Neptune and Triton. And so it looks a little bit like this. I got Neptune and Triton, and when you do the math for satellite velocity, the mass of the object on the smaller object cancels out in the math, right? And so people are sometimes confused. Why did that happen? Well, the reality is the only reason that works is because the object in the middle is so much larger that the radius here in the FC equation is the same as the radius in the FG equation. And you might be going like, "What are you talking about, Mr. Morrison?" Um, in this case, the Neptune, which is 1 times 10 to the 26 kilograms, and Triton, which is 2.1 times 10 to the 20th kilograms. Neptune has got 6 more zeros, so that's a million times more massive. And so, even if you go to Earth is 6 times 10 to the 24th, and let's say there's the International Space Station, right, which is I don't know, maybe like 1 times 10 to the a fifth. I don't know. So it's like maybe 10,000 kilograms or something like that. It's not going to actually alter the path of the Earth. It's almost like the Earth is anchored and the objects are going around. Now, the Earth isn't anchored, but it's so massive that the object that's orbiting is orbiting around the center of the Earth. Okay. If that happens, then these two R's are the same, and then I can make these two equations equal to each other. If I make those two equations equal to each other, then the M's do cancel, and you get this very simple equation, V equals G times M divided by R, where the M is only the mass of the center planet, and we don't really include the mass of the planet on the outside. So, but what if the object was bigger? How would that change it? And so let's go ahead and look at how that would change it. So here I have two examples, or an example here of an object which has a mass that is twice as big. So I got 200 on the left and 100 on the right. And so if the object is twice as big, the object on the outside won't actually revolve around it. They'll kind of revolve around each other. So if you go to, I think it's Tatooine in Star Wars, that has a binary system which has 2 stars. Those 2 stars are not just sitting in the center of the solar system. Those 2 stars are actually rotating around each other with sufficient speed that they don't come together. Otherwise, they would come together and make one massive star. If you could picture a flimsy water balloon and just wing it and throw it in the air, it will spin. And as it spins, it kind of like if it has like, whoop, it'll kind of roll tight around each other. Maybe like two balls tied together, and you threw it in the air, it would spin around each other. But if one ball was bigger, what would it spin around? And if one ball was bigger, it would the center of the radius would be closer to the bigger ball. So here it's pretty simple, because if this distance between them is 300, right? If this one has a mass of 200, this has a mass of 100, then the distance where it spins around and rotates around will be 100 on this side versus 200 on this side. So the distance will be that center right there. You can do the math for that using our center of mass equation, and you can see how that's true. Since these two objects are turning, they're always going to be exactly opposite of each other in their rotation. And that's just the rotational dynamics of how this works. So in this case, if this happens, the object, which that's hard to see, the object here on this side is going to be going slower than the object there on that side, because the one on the outside has to go faster, and the one that's on the inner circle is going slower, always keeping each other exactly opposite of each other. And so this one makes a smaller circle going slower, and this makes a larger circle going larger. In this case, the circle is twice as big versus half as big, so you can kind of see what's happening to the velocities there, which makes sense because they're always opposite of each other. But that's pretty interesting. But we actually have an example in real life, and this is the star system, which is a binary system in the Milky Way. It's called Sirius A and Sirius B. There we go. And so many things are set up so nicely here. Sirius A is twice as big as our sun. Sirius B is the same size as our sun. Our sun happens to be 2 times 10 to the 30th kilograms. So if you look on there, we have 2 times 10 to the 30th kilograms here. And then we have twice as big is 4 times 10 to the 30th. So A is twice as big as B. The distance between them, now in real life, it's an elliptical orbit. And I've drawn it as a circle, which makes the math easier. But the distance between them is 3 times 10 to the 12th. That's the distance between them, 3 times 10 to the 12th. And that's easily divisible by 3, which makes it nice because this is like 1/3 of the way. And this is 2/3 of the way, right? This being twice as far as this. So the distance of this from the center, and it's rotating around the center of mass, is twice as big as the distance to the center of this one as it rotates around the center of mass. And remember, they're always going exactly opposite around each other. And they're rotating around a point in space. They're rotating around each other, but the point in space, which if you drew a dot, that would be the center of the radius, would be right there at the center of mass of the system. And so the nice thing about this is these are real items, and we can really get real numbers out of this. So how much force is pulling them together? That's the first question asked. There is a force on them called gravity, and it's pulling at the full distance. So the force of gravity is going to be 6.67 times 10 to the negative 11th, which is G, times the mass of the first planet or first star, Sirius A, which is 4 times 10 to the 30th, times the mass of the second, which is 2 times 10 to the 30th, divided by the distance between them squared, which is 3 times 10 to the 12th, squared. You take that and you get the force of gravity between them is 5.93 times 10 to the 25th. Now, that's the same gravity on each one. It's like Newton's third law. You pull me, I pull you, right? And so the force of gravity is always the force between two objects, Sirius A versus Sirius B. So the force of gravity between them is that. So now we solve that. That's actually the average force between them as they go through their orbit. That's the average distance as they go through their orbit around each other. It's an ellipse, so sometimes they're farther, sometimes they're closer. That's the average distance. I've got mine in a circle, so I'm just using the average. Okay, now I'm going to use the equation which we had before, which is the centripetal force equation, Fc equals mv squared over r. And just realizing that the radius changes. The radius is not the same. Hold on. Also realizing that which mass do you use? Well, in this case, we're talking about the mass that's actually moving. And so in this case, we rearrange to solve for the velocity of the object as it goes in its orbit. So this one on the left is A, which is the velocity is going to be the square root of the force between them. Remember, the force between them is the same. And now I did the same thing over here. So the force between them is 5.93 times 10 to the 25th, which is the same here, times the radius. Now, the radius of this one is 1e12, and the radius of this one is 2e12. 2e12, right? The radius to the center of their orbit, divided by their mass. The way this works, remember, it's different than the other equation, which is derived differently from the notes today. The mass of this one is twice as big, 4e30 versus 2e30. And if you look at it, you get the velocity of 3850 meters per second versus 7701. Now, if you do this exactly, you're going to get a ratio, and the ratio is exactly like we said. It's 2-to-1 ratio. Let's look at a bunch of things here. If I can move this. When we do this, because this mass is twice as big in this binary system, then we got these real simple ratios here. The mass is 2-to-1. The radius is 1-to-2. The velocity is also 1-to-2. Remember, the one on the smaller one has to go faster in order to make the bigger circle at exactly the same time as the larger one. And the forces are the same. The reason the forces are the same is because the force of gravity between them is the actual forces pulled together. Now, if you try to verify this online, go like, hey, I wonder if these numbers are actually pretty legit for online, because we'd like to be able to verify, is the math that we're doing in our physics class the same as real world math? And so if you look at this, it's an ellipse. So it's going faster and faster as it gets closer, and then it goes slower and slower as it gets farther apart. And so there isn't a velocity. So this is a velocity if it was going in a exact circle. The average velocity of the ellipse is 7.5 kilometers per second, which is 7,500 meters per second for Sirius A, and 15,000 meters per second for Sirius B. And if you notice there, it's still the same ratio. It's not the same values because of the ellipse, but it's still the same ratio. So that's actually pretty cool. Hopefully that gives you a little bit insight into why, you know, um, this one we can get rid of the velocity. We can get rid of the velocity because the radius is the same. And because really, in essence, it's because the one object in the middle is super large compared to the one on the outside. Now, anytime even if you compare our moon to us, our moon is like times 10 to it's times 10 to the fifth. I think it's like one, I can't remember what it is, but our moon is really large. And so the moon is not revolved around the Earth. We are definitely in this interaction where the center of mass of the moon Earth system it's actually still within the Earth, I believe, but it's more toward the crust. So I figured that out before. I think I show it later on, maybe somewhere in a lecture. But kind of interesting. The larger the mass, the less true this equation is. But at these real small mass comparisons to the center, this equation works great, works perfect. You can look it up online, and it's good to go. So anyway, yeah, that's it. It's a pretty cool way to look at it, and you can see that hopefully it all makes sense now. And what a great example to have Sirius A and Sirius B have such easy numbers to be able to work this out. So anyway, as a little rabbit hole for you, and I'll talk to you later.